of sine and cosine functions. So we're fairly familiar with the basics of the sine wave and the cosine wave. They are periodic functions. That means they repeat themselves. It's a pattern that repeats over a certain period length. And today we're going to talk about how we can transform them, how we can move them left to right, how we can stretch them, compress them, move them up and down. Factors, A, K, D, C. I call them parameters. They guide the transformations that we can apply to any sinusoidal or periodic function. So here we go. Your first one is already given for you. If A, so that's the multiplier out front, maybe we should write down the equation. We're not going to have any space anyway, but maybe I'll write it up here. We've got y equals A times the sine of k x minus d plus c. Okay, there's our basic equation for transformations on a sinusoidal function. Okay, so now we know what we're talking about. A is out front here. Just like in other types of functions that we talk about, this is going to stretch it vertically and vertically. And so what we say here is actually this dictates the amplitude. So here, amplitude is greater than 1. And that's going to cause a stretch, right? If the amplitude is 1, then it has the standard, max at 1, min at -1. And if we raise the amplitude, if we make A 2, let's say, well then all of a sudden it's going to have a max at 2 and a min at -2, and it's going to be taller and skinnier. But notice it's still going to cross the x-axis at the same point. So it hasn't stretched or compressed horizontally, only vertically. Okay? Let's look at what else A can do. Here the amplitude would be between 0 and 1. So this is going to cause a compression. So if I do our same drawing quick, we normally would have a max at 1 and a min at -1. But if we had a value of A of, let's say, 0.5, then all of a sudden we'd be crossing at the same point, but we'd only be going half as high. And crossing at the same point, but only going half as low. All right? So that would be a vertical compression with an amplitude between 0 and 1. Now, if we end up with a negative amplitude between 0 and 1, it's going to do two things. It has an amplitude, amp between 0 and 1, but it's also negative, so it's going to cause a reflection in the x-axis. Reflection in the x-axis. And some of these boxes you're going to have to squeeze the information in a little bit. And if A, so that would be, it's a compression, so it's shallower, but it's flipped right upside down. Okay, so that one's going to look like that. And then if we go for an amplitude that is less than -1, so its absolute value is greater than 1, but it's in the negatives. And so it's going to do two things. It's going to do a stretch, vertical stretch. So we're going to say that it has an amp greater than 1. And it's going to be a reflection in the x-axis. So again, that's going to be, here's our original, up to 1, down to -1. We're going to be doing the same crossing point, but it's now going to go upside down, down to -1, then up to +1, and carry on. Okay? So you can actually kind of see, you can start to make some pretty cool designs if you graph these functions on top of each other. Let's take a look at the parameter k and how that's going to affect the graph of a sinusoidal function. When k is greater than 1, what happens is the period gets smaller. So as k gets bigger, comma, the period gets smaller. So what does that
It's
mean?
because
Well, the relationship between period length and k is p equals 360 degrees over the absolute value of k, and we'll typically just use k in this little formula. But what that means is that the typical period length is 360 degrees, right? The time it takes for the terminal arm to make one full rotation, and therefore the graph to make one full cycle, is 360 degrees. And because of the relationship, horizontal compression or stretch by a value of 1 over k, that's what's happening here. It's one cycle divided by k. And so as k gets bigger, the period length is going to get smaller. So if this k were 2, then our period length would be 180 degrees, and we'd actually complete 2 full cycles of the pattern between 0 and 360. If it were 0.5, then we would have 360 divided by 0.5, which would make the period length 720 degrees, which means you'd only get half of a cycle done between 0 and 360. So there's the relationship there between P and K, and we'll be working on that much more as we work through the rest of this unit. What else happens? If K is in between 0 and 1, we can note that the period gets bigger as k approaches 0. And that's just the opposite of what we wrote above. The period gets bigger as k approaches 0. Basically what that means is as your denominator gets smaller, the fraction as a whole gets bigger. So as k tends toward 0, if it were 0.2 or 0.1 or 0.05, as it gets smaller, the period length is going to get bigger and longer, and this thing's going to get more and more stretched out. Okay? If it is between -1 and 0, then we can say the same thing as above. So we'll just go as above. And what happens? It is actually a reflection in the y-axis because k would be negative. So it would flip this thing over the y-axis. Reflection in the y-axis. Now, what's interesting about that one is, let's say we have a sine wave. Sine wave, if we flipped this over, it would certainly look different. But if you took a cosine wave, which has its max at 0, something like that, and you flipped that over the y-axis, well, look what you'd get. You'd get the exact same thing. So reflecting cosine wave without sliding it left and right over the y-axis results in the exact same wave as its original, whereas the sine wave is different. But notice it's actually the same result as flipping it over the x-axis. And these two illustrations demonstrate a character of each of these graphs that we will be looking into further as we move along, a property. Okay, and our last one for the parameter k, if k is less than 1, then we have the period length getting smaller. So period length gets smaller. Implied there is as k, the absolute value of k gets bigger, or as k gets more and more into the negatives beyond -1. And we know here there is a reflection in the y-axis. All right, so those are our multiplying factors, our multiplying parameters. A is going to vertically stretch or compress and reflect the whole function, okay? K determines what's happening to this thing horizontally. Again, you can stretch it, compress it. It's going to change the period length. You can also flip it over the y-axis. And now we move to the parameters that are either added or subtracted, okay? So these guys, again, are just going to move this thing. They're going to translate it. So here we go. And we don't, in sinusoidal functions, we're going to stop using the word translation, although you'll hear it slip out every now and then by accident. It's called a phase shift. So I'm going to call this guy when D, which is out inside the brackets here, affecting X, affecting the horizontal situation, is going to be when D is greater than 0, it's going to be a phase shift right. Okay? So we're used to calling that a horizontal translation. We'll put that in brackets. And again, we have to remember that if D is positive, then inside the bracket will actually be X minus some number. So when we see X minus some number, we're actually causing it to phase shift to the right. All right, and same thing when you see X plus a number, that actually means you have a negative value for D, which is going to cause a phase shift left D units, right? That's a horizontal translation. All right, last one. C is going to affect just the vertical. It's a vertical shift when we're talking about sinusoidal functions. It's way outside here, it doesn't change the shape, just moves it up or down. When C is positive, we have a vertical shift up. So we're used to calling that a vertical translation. And when C is less than 0, that means negative, we have a vertical shift down. All right, so today is all about working with these parameters, modifying or transforming some of these sinusoidal functions, and actually your homework for today is just a investigation, basically a graphing assignment with some of the same things going on here. So if you're a hands-on learner or visual learner, that'll help as well. Okay, in example 1, we're just going to be working with the parameters A and K. Those are the multiples, so they're the stretch, compression, reflection parameters here. And we're just going to be looking at the example that they give us and determining what are some of the characteristics of this graph. So the one that we're working on is 3 times the sine of 4x. Okay, so amplitude, that's determined by A. It's the absolute value of A. So this has an amplitude of 3. Okay, it's given to us right there. Period. Now we have to remember that the relationship between period length and K is 360 degrees, which is standard period length for a sinusoidal function, divided by K. So the period length here is 90 degrees. That means every 90 degrees, this pattern is going to repeat itself, which means that between 0 and 360, it's going to repeat itself 4 times. And you can see now the number of cycles between 0 and 360, that is the value of K, okay? The absolute value of K. If K is 4, you're going to get 4 cycles. Each cycle is going to be 90 degrees, okay? To graph this, I'm going to graph this 2 different ways. One way is the fast way, and one way is the slow way. First, I'm going to show you the slow way, okay? So I'm going to do this little cheat here. I'm going to try to do my best curve, and then I'm going to draw my x-axis right through the middle of that, and because it's a sine wave, I know it miss. I know it's going to start right there. Okay, so green indicates the typical sine wave. Let's see what we're going to do to this thing here. We're going to give it, oh boy, I did a mistake because I'm not going to be able to fit mine, but I'll try it anyway. So we're going to have an amplitude of 3. So what's that going to do? That's going to say if this is a max of 1, 2, 3, 1, 2, 3, and let's go for our minimum, 1, -1, -2, -3, -1, -2, -3. You can slide this up for us so you can see what's going on here. And we're going to have these same x-intercepts, but now we're going to go all the way up to +3 before coming back down. Okay, And a tip for drawing these things, it's kind of a fat, wide U. Okay, so it's kind of flatter when it hits its min, and then it comes up real fast through the same point that the original did, up to +3, and back down through the same point that it did, and down to -3. All right, so here what we have, if I'm taking our original here, we have, this is 360 degrees. This right here is 180 degrees, which makes this 90 and this 270. Okay, so you can see we in green and red, though we've stretched it vertically, we're still completing one full cycle in between 0 and 360. Not sure what I was thinking with that curve over there. Now we're going to apply the K of 4. And what that does is it now is going to do a vertical compression by a factor of 1/4. So our period length now is going to be 90 degrees. And look at how we're affected here. So that means that instead of completing one period length by 360 degrees, we're going to be completing one period length by 90 degrees. So in between 90, which is 45, I'm going to have gone all the way up to +3, then down through the point at 45, down to my -3, and then back up to 0. Okay, all by the time we get to 90 degrees. We're going to do that again by the time we get to 180. So I'm going to draw a little indicator there. I want to go up to here, back down. It's just bad drawing that these maxes lined up at the same spot. They really shouldn't. This max should be at 90. The red max should be right up there. Anyway, and I'm going all the way down and back up to 180. 2 cycles right there. Same strategy. By the time we get to 270, we're going to have completed another cycle. Down, up, and by the time we get to 360, we've got our 4th cycle. Right about there. Okay, so now I've drawn 4 cycles between 0 and 360. This is, the blue graph is what y equals 3 times the sine of 4x will look like in comparison to the unchanged graph of y equals the sine of x indicated by the green here. Okay, that is the way to do it if you really want to see what this looks like with the same scale that you're used to always using. Now, here's a cheeky little secret that you can use whenever you're sketching these. If it tells you to transform the function from the base function, then go ahead and do it that way, the way that I just did it. But if it doesn't, then just go ahead and draw your best sine wave. It's honestly the best I can do. And draw your x-axis. And to apply your transformations, you're really just going to be changing things along the scale. So this has no horizontal translation or vertical translation. So I know that sine generally looks like that. And now all I'm going to do to apply this vertical stretch of 3 and amplitude of 3 is I'm just going to say, oh, there's my max. It's at 3. And there's my min. And it's at -3. There, I stretched it with an amplitude of 3. And, 4 period lengths in between 0 and 360. And each period length is 90 degrees. Well, from my start point, up, down, okay, that's 90 degrees then. Yeah? And backwards 1 period length, that's -90 degrees. Now, if it asked me to graph the whole thing between 0 and 360, which this one does, I didn't actually end up accomplishing that. I would need to keep going. Okay, so I need to be aware when I'm doing this of how much space I need. But basically, I could have drawn any curve that I wanted to, and then indicated that the max and min were at 3 and -3, and that each cycle would be done in 90 degrees, okay? So I didn't quite fit on the 360 degrees, but you can see how this works real easy if you draw your curve first. All right, example 2, we're just working with the vertical and horizontal shift in this example. So amplitude is really easy. Standard amplitude of the periodic function is 1. Period length, again, it hasn't had a horizontal stretch compression, so we're looking at a period length of 360 degrees. Phase shift, sorry, I should write down the example that we're actually looking at here. We're looking at the sine of x minus 45 degrees plus 2. Okay, so the phase shift here is going to be positive 45 degrees. So we're going to be moving 45 degrees to the right. Okay, vertical shift, we're adding 2, so we're going to go up 2. And here's an interesting one that we need to pay attention to. The rest of the sinusoidal function is typically, right, it's that point that it hovers around, it oscillates about. It's typically 0. We've moved this whole thing up 2, so the new rest is y equals 2. Okay? And now we get to go ahead and graph it. We're going to be graphing it from 0 to 720. And I'm going to start the same way that we did before. I'm simply going to be a little bit more mindful of my space this time, but there's the graph of y equals the sine of x. Yours will hopefully be a bit prettier. And I will draw my x-axis. There's our y-axis, and maybe I should just put it right over here. Okay, so now I know I have 360 there because one cycle is done, and I have 720 there. And now let's apply these translations. We need to shift this 45 degrees to the right, okay? Let's look at what that would look like. Basically, if this is 360, then this is 180, 270, 180, this would be 90, okay? So I'm not shifting it a whole, it would be easier if it was a shift of 90 to start us off, but we've got a shift of 45. So basically all I'm doing is I'm pushing this key point 45 to the right. I'm pushing this key point 45 to the right. Okay, that's actually not a very good drawing. It should be there. I'm pushing this key point 45 to the right. I'm pushing this key point 45 to the right. This key point 45. Okay, you see what's happening here? And the whole thing, it's going to end up looking like that. Comes up. There's no stretch here, so my max is still 1. But our x-intercepts have all moved 45 degrees to the right, as have all of our maxes, right, and all of our mins. Okay, and I'm just using little sketch lines here. Again, your graphs will look a little bit neater, but you can see how the purple is just kind of following the green. But it's, I guess the green is following the purple since we moved it ahead. We shifted it to the right. And there's 720 degrees, so we're good there. And now the last thing we need to do is shift this whole thing up 2, okay? So instead of having the rest at 0 and the max at 1, we're going to have the rest at 2 and the max at 3, all right? Well, let's look at what that looks like. And what's that going to do to our minimum? Well, our minimum is going to be at 1 then. So typically what I would do here to help myself think this through is I would draw a dotted line across with my ruler at y equals 2, and I might even just indicate that that's y equals 2. That's our new rest. And now we're going to just kind of translate these points straight up vertically. All my key points are going to go up 2 units, okay? Do my x-intercepts first. I'm looking at the purple line here, purple curve, straight up. Again, it's easier when you have your graph there. I don't have any squares here, a grid to follow. So I'm just guesstimating. My minimum is going to be at -1. And now minimum and maximum are a little bit easier once you have your x-intercepts in. Because look, the max is in between those two, and then a min in between these two, and then a max. And if I didn't have a grid here, which I don't, I could do a dotted line across for my max as well, so that I could just keep my proportions proper. But there we go, that's enough. Here's a curve through my new rest, down to my min, back up. And there we go. Okay. There is a sketch of y equals sine of x minus 45 plus 2 as it relates to our original sine function, which is there in green from 0 to 720 and a little bit extra. All right, example 3. This time we have all 4 parameters worked into here. Our function that we're going to be studying and drawing is y equals -2 times the sine of 3 times x plus 30, close bracket, minus 1. All right, well, let's work through this piece by piece, and then we'll think about the best way to graph this, all right? So we've got an amplitude, remember, of the absolute value of a. So right now, just indicating the amplitude doesn't pay attention to this negative sign. The amplitude here is 2, okay? If you want to at this point, you can indicate that there's going to be a reflection over or in the x-axis, okay? Period length, remember the relationship, we're going to have 360 over k. So we're going to get 3 cycles in between 0 and 360, which means each cycle is going to be 120 degrees. We're going to do a phase shift. This is a phase shift of -30, so we're going to be going left 30 degrees. We have a vertical shift down 1, which gives us a new rest of y equals -1. And now we're going to graph it. And before we do that, we're just going to think about this, and we're going to see if we can do it with a, I'm just going to draw the curve and see if we can do a little bit of cheating here. I think I have enough in there. We'll see when we get there. But let's think about where our x-axis is going to be. So our rest coming across the middle here, I'm doing it in a dotted line because it's not going to be our x-axis. This is actually going to be y equals -1. Okay. And if we look at our amplitude of 2, that means that this maximum here, if I just kind of indicate this, an amplitude of 2 would give us y equals 1 as a max, and y equals -3 as a minimum. Okay, so we've got a good idea of where our x-axis is. If I have my ruler out, I could do a real nice line here in between my max and my rest. I'm a little high there, but you get it. That's our x-axis. And for our y-axis, we need to think about how many cycles are going to be completed. And really, actually, we can think about that when we put our numbers along the x-axis. But what we really need to know is its phase shift left 30. So now sine will typically cross its rest right here, okay? Or right here. So that's where we would draw the y-axis, but we're saying that we're shifting this whole curve, the pink curve, 30 degrees left. Now back to thinking about the period length being 120 degrees. 30 degrees left is 1/4 of the period length, okay? So if we think about this period length from here to here as a whole period length, this is half a period length. the max of sine occurs at 1/4 of the period length. So our new drawing, remember if our curve is going to be moving to the left, then relatively speaking, the y-axis is moving to the right, since I'm kind of drawing this backwards. But now you can see how the curve, the sine, typically would come from here. It's now being moved 30 degrees that way, which with a period length of 120 degrees is 1/4 of the period length, okay? We still don't have the right thing because I left out one important piece of our drawing, and that is this little negative sign, okay? So maybe first we'll add some numbers here. We have 0, of course, and 1 full period length, so the maximum here. 1 full period length is occurring at 120 degrees, and then 240 degrees. And if we bounced up again to a new max, we'd have 360 degrees. Okay, those are 3 cycles between 0 and 360. But again, we haven't dealt with this vertical reflection, this reflection in the x-axis. So now I'm just going to go ahead and do that. So instead of a max here, that's where we're going to have our min. Instead of a min, we're going to have our max. Instead of a max, we're going to have a min. Instead of a min, we're going to have a max. And we can do that dance all the way along. Our rest intercepts, where we're crossing the rest, isn't going to change at all. Here we go from our min up, rounded tops, remember, for our most accurate drawing. That was a bit aggressive. And if we finish that all the way out, we will have 3 cycles between 0 and 360, indicated by this blue graph here, and y equals -2 sine 3x plus 30, close bracket, -1. Okay, so when you're doing these and you're starting out and you're practicing, it's probably best to draw the standard sine curve, then apply the transformations. Okay, once you get really good at it and you can think about it in different ways, you can start to do it this way. With all 4 parameters plus a negative sign in front, this was pretty tough. I probably wouldn't do it this way again. Maybe I'd do a couple of them and then start transforming from there. I actually did that with the negative sign, right? We did the negative sign last to flip it over the x-axis, over its rest. And we've only dealt with sine. So you have to remember that in your practice problems, you're going to be doing some with cosine as well. And the only real difference is right off the start, cosine has its standard x equals 0 at its maximum, and it will cross, it has a y-intercept at 1/4 length of a period, which would be 90 degrees, an x-intercept, and then it comes back up, and this will be 270, 180, and back up to the max at 360. Okay, whereas sine starts at 0, 0. It doesn't start or stop anywhere really, but it starts at 0, 0 and hits its max at 1/4 of a period length, which means it's going to cross 0 again at 180, hit its minimum at 270, and have its last x-intercept at 360. Okay, so the difference between here and here, which we'll learn along the way, is 1/4 of a period length. Standard isn't going to be 90 degrees, but for instance, if we change our period length like we did over here, 1/4 of the period length ended up being 30 degrees. Okay, that was 1/4 of the period length, which helped us as a reference when we were moving this one. But that's the difference between sine in black here and cosine in blue. So just be careful as you're drawing those, transforming them, see which one you're working with. Start with the base function and apply the transformations one by one. Your practice for today is actually just completing the transformations of sinusoidal functions assignment, which is posted for you on Pigeon.